Hey y'all, welcome back to another exciting day of calculus. This video is the warm-ups for lesson 4.04, the mean value theorem. But before we actually get into that lesson, it'd be a good idea to warm up our brains with these couple problems here. So number one, it gives us a derivative. It says f prime of x is equal to negative cosine squared of 3x minus 1. And it is asking for how many relative extrema we have. Well, think about what a relative extrema is. A relative extrema is any high or low point on the function, not on f prime, but on f of x. And so we've gone through the motions of trying to develop where we find relative extrema. And if we think through it, the bottom line is we are looking for, if the function is continuous, we're looking for when the derivative changes signs. So this is actually a pretty easy problem in the answer. The answer is simple because of a particular situation this function offers. But not all functions are like this. So I'm going to want to go through step by step of what to do with this, and then we're going to see, oh, this answer just makes sense. But it does give us an open interval of 1 is less than x is less than 4. So we're looking for any extrema within that interval. Now remember, to go through the process of finding relative extrema, the first thing we have to do is find critical points. Critical points are when one of three things happen. Number one, the derivative is equal to 0. Number two, the derivative does not exist. Or number three, at endpoints. Well, in this particular case, we are talking about an open interval. So there are no extrema at the endpoints because there are no endpoints. We're not counting those. So we're going to go through and find the other critical points. And that is when the derivative is equal to 0. Well, we're given the derivative function here, so we don't have to take the derivative. We just set that function, that derivative, equal to 0, and then solve it from there. So we can solve this. And normally I would suggest just using a calculator at this point. Type it into your TI-89, type this into your Y-list, find the zeros. You're going to find that there are actually quite a few of them, and we would just list them here. I'm going to kind of go through a little bit of this. First thing, if I'm going to do this analytically, is I'm going to divide by -1, and then I'll take the square root. But the bottom line, when I do that, I get 0 equals the cosine of 3x minus 1. And so from here, we would ask ourselves, when does cosine equal 0? Well, cosine equals 0 at pi over 2, at 3 pi over 2, at 5 pi over 2, and so on. And then we also want to look in the negative direction here. So that would be the case when the theta, the angle inside the cosine, the 3x minus 1, is equal to pi over 2, 3 pi over 2, 5 pi over 2, ... And then also when 3x minus 1 equals negative pi over 2, and negative 3 pi over 2, and negative 5 pi over 2, and ... Now, the good thing is we don't have to check on forever and ever and ever. We're just looking for the interval between 1 and 4. So we would solve these equations and see which one of those offer the interval between 1 and 4. Then we would look for other critical points. So we would list all our critical points. We'd say when x equals this, and this, and this, and this, and whatever critical points we have. And then we'd also look for when f prime does not exist. Well, a cosine function always exists, so we're not going to have any discontinuities in the derivative, so the derivative will always exist. We're not dividing by 0 or anything like that. So our critical points are, in this particular problem, are only when the derivative is equal to 0. So we can have a whole list of them. But remember, the next step in figuring out critical points is figuring out relative extrema is to determine when the derivative changes signs. This function is a continuous function. The derivative is continuous. Therefore, the function must be continuous as well. And so all we have to do is figure out where the derivative changes signs. So whatever solutions we get here, we would set up a number line for all these different x values. This is when the derivative is equal to 0. And then we check the signs for all values on either side of that, either side of those intervals. In this particular problem here, this derivative is a negative cosine squared. And so really, it's not going to matter what we plug in because cosine could be positive or negative. The cosine of a number can only be between -1 and 1. But when I go to square that, that means my answer is never going to be negative. It could be 0, and that's where these zeros come into play. But it has to be a positive value there, and then when we multiply by a negative, we get a negative. So that means the derivative will always be negative or 0. So whatever these critical points are, our derivative will be negative in between those values, no matter what. No matter what. We can look at our endpoints from 1 to 4, but because we're squaring this function, the derivative, f prime, will always be negative or 0. And since we're looking for relative extrema, we're looking for when the derivative changes signs. Well, it never does. So how many relative extrema do I have in this particular function? We have none. We have 0, since f prime never changes signs. So that's just a good logical problem. That should only take a few seconds to figure out, because you wouldn't have to go through all this work. But if it was any other function, if it was like cosine cubed or just cosine of 3x minus 1, then you'd have to go through all this work, and I would highly recommend just getting a calculator, finding those zeros, taking those critical points, lining them up, and then figuring out the signs in between each of those intervals. Okay, so for number two, we're given a graph of f prime, and that's important. We've got to pay attention to the graph that we are given here. So I'm not going to be able to draw a perfect graph here, but it comes down like this, and then back through like this, and then up, and then down, and then like that. Okay, so it's asking, when is f decreasing? Well, again, keep in mind that this is the f prime graph. Okay, it says that this is f prime. So let's go through our justification. We know that f is decreasing when f prime is negative. Okay, so f is decreasing when f prime is negative, and that's according to the chart that we're developing throughout this unit. So we would just look for when f prime is negative. Being that this is the f prime graph, we are looking for when f prime is below the x-axis. If this was f, then f is decreasing when we see this function going downhill, because this is f. But this graph is f prime, so we are looking for when f prime is negative, below the x-axis. Let me throw some points in here. We've got, at this end, we've got -7. This point is -6. Then we obviously have 0. We've got a -3 for this low point here. We've got 3 and 7. And then out here, we have a 9 for that endpoint. Okay, but again, this is a pretty easy problem. F prime is negative when f prime is below the x-axis. So that's pretty easy to see. We would say, therefore, from -6 less than or equal to x less than or equal to 0. And that is our answer for number 2. So go ahead and stick around for the next video, which is about the mean value theorem. Sounds kind of what it says, the mean value theorem. Mean, another word for mean, is the average. So we've been talking about calculus. Average is all about average rate, average slope, instantaneous slope. So how does the derivative that we've been talking about so much this year, how does the derivative relate to the average slope? So stick around for that video. Hopefully you're excited to watch it just as much as I am to present it.